gonna record this lecture.
Right. All right.
Good to go.
Yeah, let me let's see. 1 second, sorry. Let's try doing this. Well, I was gonna turn on my video, but it seems like it's a little complicated. I'll just go straight to sharing screen. Hi, everyone. Hope everyone's having a good meeting so far. And I'd like to share just a few things. I've been working with colleagues. Not sure if everyone is there, but it's been a really fun and inspiring discussion and journey so far, thinking about how we can use virtual reality in geoscience education to really increase accessibility. And I think really, I would say almost everyone is a geoscientist in a way. It's just really everything around us and our interaction with the material on our planet as well as other planets. And geoscience is critical to our present and our future. I mean, this is really our only home. Don't have any other place to go yet. But staying in our home and keeping it habitable is a challenge, really. And so there's a number of really grand challenges for us to consider. And how are we going to train the current and next generation of geoscientists to really help resolve some of these challenges? So there are many hazards. The Earth is a magnificent place, beautiful place, inspiring, but there's a tremendous number of natural hazards. For example, there are volcanoes, and there's volcanoes really across the planet. They're clustered and they're concentrated in certain areas because of certain Earth processes, but it's really important to be able to observe these features, to characterize their behavior, and to understand, the hazards they pose. Just a little snippet here of volcano called Fuego on the top right, and on the bottom right, this is actually volcanoes that erupted through a lake in Eastern California. On the left here is just a photograph I just snapped of, or I didn't snap it, but I copied it from the US Geologic Survey's website when I just searched volcanologist. So I thought it would be interesting to also think about what are the representations of these geologists when we just search for their images. And, interestingly, there's also seismic hazards. And I wasn't able to experience the recent earthquake in New Jersey, but there's a need really to understand plate tectonics, to understand the rates of movement, the history, past history of earthquakes along certain faults where there's, to better characterize, for example, building codes. And this is on the left, a map of seismic activity in the US and where there's population centers. So you can see where there's, on the East Coast, there's really large population centers, and really understanding these seismic recurrence intervals is important. And then places across the planet where there's enormous, large fraction of the population on the planet, like in East or Southeast Asia, where the seismic hazards are much larger. And we can measure these movements of the plates with GPS data. On the top right is just some of these places where you can stamp and place these receivers that you can measure their movements, even in the vertical sense, not only horizontal. You can measure that across years to look at velocity. And that's what you're looking in the bottom right. Those arrows are showing velocity. And as a geoscientist, one of, I think, a remarkable skill that you get through geoscience training is the ability to tell stories of the past. And in the geologic record, we have over 4 billion years of Earth history to try to understand the evolution of the planet, the changes, and also to think about how these past changes on our planet may inform our future, in particular, for example, about our climate future. So there's really a need to understand the past. And we are interested in not just understanding little snippets of the past, say, for example, changes in past temperature, changes in plate tectonics, but also to think about one of the grand challenges actually is understanding ice ages and how they terminate, because terminations, or when these ice ages end, they end very fast. So ice ages can span for tens of thousands of years, but they usually end in a fraction of the time, a few thousand years at most. And that may indicate that there is something nonlinear in the system, and perhaps about how ice sheets behave and how they may collapse rapidly compared to their interval of growth. And that's important today to think about for the fate of the Greenland ice sheet, the fate of the Antarctic ice sheet, sea level, and being on Long Island. That's really important. It's going to be really important, and it is today. What is sea level going to do? Now, here's even some remarkable things you can do with other parts of remote sensing. So on the bottom right is this GRACE satellite, which measures gravity across the planet. And on the top right, you're seeing a time series through time of actually observations that you can do remotely of the mass balance of the Greenland ice sheet. You can actually quantify the changes in the ice sheet's volume over time. And you can see it's been losing water from 2000 to 2016, and this is only going to continue, and it's going to accelerate. And on the bottom left is something I want y'all to just look at. It's a front cover of Science magazine, highlighting an application of this GRACE satellite to measure the changes in water storage, so the subterranean water storage, following the most recent sort of big drought in California, which was sort of in the mid-2010s. And as a result of this drought, there's a lot more groundwater pumping, and then there was an associated change in the gravity that was measured. And so you can actually see here, it says the drought that you cannot see. And so I'd like to use that as perhaps an allegory, a metaphor for some of the other things that we can't see in our fields, and why that's a problem. And so there's really a big problem with accessibility in the geosciences and equity and inclusion. It's really amongst the least diverse STEM fields. And adding to that, even more so, individuals with disabilities are even less well represented in general in the STEM fields, but in particular, that's true for the geosciences. And there's really a number and a vast array of systematic barriers for participation, education, and also research. The standard depiction of geoscience education is for students to be instructed in various in-class modes of teaching, and that include labs, but also field trips are really important. And geoscience as well is quite a very social experience in terms of the education. Often students may go for 1, 2, sometimes 3-day long field trips. But perhaps the most iconic feature of this education is what's called a field camp, which is a destination experience where you depart to often remote areas, rugged terrain for 4 to 6 weeks. And as you can imagine, this is a challenge. And not only that, it's not only a challenge for everyone to participate in, but it's incredibly costly. So there's these are real barriers for access, inclusion into geosciences. So I've been thinking about this problem. It's quite personal to me. I grew up and my family member in my house who had physical and mental impairments. And so I've tried to think about, really since I started geoscience education 10 years ago, what can be done here? This is not right. And really it's the responsibility of the instructors to be able to consider where they're leaving people out and how to resolve that. So I was very excited when I first started at Stony Brook in the fall, and I heard, I think at the new faculty orientation, something about virtual reality. Come to CELT, talk to us. So I think within the first week or so, I try to find out, what's this all about. And so this is kind of where it's moving towards, and I think hopefully I think in a very positive direction. I've been what do we call it? Not lent. I share. There's a 3D camera, a GoPro 360 that I've borrowed, I guess you can say, and was hoping to spend quite a bit of time in Eastern California doing field work, as well as mapping some of these areas for in-class instruction in the fall. This is a view looking northeastern California, a place called Bridgeport, looking west. The sun is there setting over the Sierra Nevada. And this is a hot spring site. And this buildup that I'm on, it's higher than the area around it, is what we term a travertine ridge. It's where subterranean sort of hydrothermal system. So it's a warm body of water beneath the surface that rises. And as it rises, it will degas and precipitate out these calcium carbonate minerals, essentially limestone. And it forms these really very cool linear features across the landscape. And I thought this would be a very interesting way to think about how to instruct some of this and have the students learn some of the key skill sets that are needed in geosciences, which is a sort of a spatial understanding how different features link up in space, how they are related, and how these features are related to a broader phenomenon like plate tectonics or volcanism. And so here's, looking very closely at, this is not the 3D video or photo, but as I was walking around trying to survey this, I was thinking, how am I going to be able to capture all the things that I'm seeing, but in a 3D, in a way that students can immerse themselves in this setting and think about how this feature forms. So this is, I was just standing earlier in the photo, just a little bit ahead. And this is the 360 camera snapshot on one of the limbs as the hot spring waters are flowing down the side. And there I am on the top left. And as the spatial organization and understanding broader phenomena like plate tectonics or volcanism is critical, but mapping is really essential. And so this is a bird's eye view of this site, and the different colors here highlight different travertine ridges, and the numbers here correspond with the age of these features. So this is in thousands of years ago. So some of these features are over 11,000 years old, and you can see that the orientation north is directly to the top here. There's different orientations of these features. And I think the other part about the education of geosciences is that everything is meaningful. Every little grain of sand, why a grain of sand is in this spot versus that other spot, or why this feature is there or not there, everything is meaningful. To try to understand, and that's really the challenge, is to make the observations and to try to extract the meaning from what you see. And the key part here is that there's different orientation of these travertine ridges. And what does that mean? And there's also different age distributions. What does that mean? And one exercise I thought about was to put the students, grant the students some of these data, have them interact with the site virtually, describe what they see, and then think about how to place these observations within a broader context. And there's no real answer here yet, actually. This is ongoing research. There may be volcanic reasons for the deposition of these travertine ridges. They may be related to earthquakes. It might be even related to climate, and that these deposits correlate with times where there's more water that's flowing through this hydrothermal system. I also went on a trip here to Owens Valley. Owens Valley is in Eastern California as well, a little bit south of the place that I just showed in the previous slides. And there's a magnificent relief in the Owens Valley, from the valley floor to the high mountaintops, which are some of the highest mountains. Actually, the highest mountain in the lower 48 is here, Mount Whitney, over 4,400 meters high. And this blue line is showing the fault, the rupturing of the surface during one of the largest earthquakes in the last 100 or so years in California. It's 1872. And I've always heard about this deposit and these features, but I've actually never visited it. But being there in person and to see it in the video is way more magnificent. This is just stepping back and looking at what we call a fault scarp, which is literally during the earthquake, the rupturing of the surface of the earth. And so what you see in front of you, this sort of inclined surface, is where highlighting the position of the fault, and the part to the away from the image went up, and the part towards me or you now looking at this photo actually down dropped. And that all happened at once. It's incredible. And you can get even closer. You can just see how large this feature is. So this is probably a 3-4 meter high exposure, and it goes on and on and on and on for kilometers. And that happened in one instance in 1872. And so, trying to be there to describe these features, not only, looking at a map and to map it, but just think about what the sediments are around here. Part of this education in geosciences is how sediments are formed, how they're deposited, how they're transported. And so there's meaning in here too, like how did these sediments get deposited in the past? And so on the left here is coming back to this map of the earthquake fault rupture in 1872, and then thinking about broadly, how does this fit in? These are the velocity, the vectors of these GPS stations and how they're moving according to reference frame. And so we're in Eastern California here on the right. And, coming back to climate and how we can do better with instruction, but potentially also even research, give these opportunities to students that would not have it otherwise. This is a cartoon, I really loved it, of a feature that you're sitting on today, which is the embankment of an ancient ice sheet. Not too long ago, roughly 16,000 years ago, there would have been mammoths near the front of this ice sheet. And if you go to the beach along Long Island, you'll see the sediments represented or corresponding with this ice sheet footprint. So on the right here is a map in this sort of opaque white showing the footprint of this ancient ice sheet and how it stretched across Long Island. The darker colors are something a little bit different, but on the bottom right, you can see these, this is a digital elevation map of Long Island. The darker colors are the higher elevation sites. And those sites are highlighting the edges or the sort of the contouring the terminus of this ice sheet. And if we can, one thing I'd like to do when I come back tomorrow actually is to, the next few weeks, is to take this 360 camera and use it to map out these wave-cut cliffs, because they're showing a succession of sediments deposited through time, and they're meaningful. They represent what has happened from the past. So here on the bottom, this orange-colored, brown-colored material, glacial deposit. At the very top is a swampy deposit, maybe some 15 or so thousand years ago, but going from ice age to non-ice age conditions. So, and something else I'd like to think about and explore is how we can inspire and to share that feeling of excitement and adventure with students, and that there's so much to think about and explore, and that's useful. So here's, believe it or not, this is actually an image from Mars, but the same principles in thinking about geosciences and interpreting the landscape and how certain features form on Earth are applicable to Mars. So there's no reason why that there should be barriers to participation for students, particularly those who, in this case, are disabled individuals, because, for example, to do the work on Mars, everyone is sharing the same from the same starting point. Everything is done remotely. And yet at the same time, everything, there's very poor representation in the geosciences. I think one of the parts that really illustrated to me that this is really a lack of not just awareness, but desire to change is during the pandemic, when everything went remote and geoscientists could not go into the field, immediately there was a massive transformation in the field, and all of a sudden all this virtual field trips started coming up, virtual instruction, and that really didn't happen before. And so it's not the capability or the means to do this is not something, there's nothing really preventing it other than, I think, a desire to and a will to do it, and awareness. And that's something I really thought about was, during the pandemic, how all of a sudden everything became available, because really the most able people were driving the change for themselves. So there's really a lot of things we can do with virtual reality. I just took a few of these snapshots, and this is actually coming back here on the right. This is actually a crater on Mars called Jezero crater. There's a delta on the center left of the photo, a river flowing into a basin filled with water. And here is a user who's actually using virtual reality to explore this feature and to map it. So there's just so much potential. And I think a significant amount of change can be done with just a little bit of effort and care. So that's where I'd like to leave off. I don't think I'll be able to see y'all, but I'll turn my video on, and I'd like to hear what your thoughts are and any questions.
Thank you so much. Yeah, if there's questions, feel free to ask. And we also have a virtual field trip actually in the headset if you want to take a look at these beautiful 360 videos and photos that Dr. Ali took.
Not really a question, more of a comment, that I never really thought of VR in terms of making education more inclusive, but I really love that that was your driving force for what you're doing, because I think that is great. So.
I didn't hear the very last parts.
Oh, I just said I think it's great that that was your driving force for what you're doing.
Absolute. Thank you.
You.
Yeah, so real quick, I do have a question for you. You had mentioned that in particular with these field camp trips, there's a huge barrier to entry there financially in particular, that it can cost up to thousands of dollars. Not to play devil's advocate, but these headsets aren't cheap either. Like a lot of this tech isn't cheap either. So is there a huge offset in the cost between the two methods?
That's a great question. My thought would be yes, that the virtual reality headsets are costly, but their use would have a wider impact for potentially multiple people and in multiple different settings, classroom settings, research settings. I think Jenny told me that the price was a few thousand for a few headsets. Is that correct?
No, $299.
Today.
$299, yeah,
Okay,
the Quest
Two-
2. Quest 2.
Two-
Quest 3 is like $599. This is Quest 3.
So that's definitely less than a couple $1,000s, so okay.
Yeah. So on an individual unit, I guess yes, it's more effective, and it can be reused. You know, the payment for the field camp is a one-time ticket. Of course, there's experiences and stuff that come with that, but the same can be true, or you can use it to produce something similar with VR.
That's an excellent answer. Thank you so much.
Mhm.
How did it work administering this? Did you have it, was this done in class? Did students use headsets one by one? Did they all get headsets? Was it done as like a scheduled activity? I'm just curious about how you integrated it.
That's a great question. I think we're still in the pilot phase. We haven't used VR yet in the classroom. I think the current plan is to do this in the fall semester in my Introduction to Geology course, Introduction to Physical Geology course. And we are really just starting to think about the lab instruction or class instruction. And we've discussed with prior examples, but I'll let some folks there chime in as well.
Yes, like some of these 360 photos, you don't really need a headset to have these. May not be as immersive as like you're standing in this picture. You can view them through online, we can find some free hosting sites for the photos, but not sure about the videos. Videos you can put on the YouTube, but it won't be the same. Yeah.
But the photos, can they be manipulated if they're online?
Yeah, you can rotate it so you can see the different angles. It's a sphere.
And what are your class size generally?
The class that I'm teaching, it's in the teens. So the last class in the fall was something like 18. It's less than 20 students. The class was for majors. There's another Introduction to Physical Geology that's much larger, but this would be for less than 20 students.
Have any students watched the videos yet? And have you gotten any feedback from them?
No, we have not had the chance to show any students yet or get any feedback about it. These trips that I took to California to record the videos, take the photos, those were done in February. But the plan is to introduce to the students and also to have surveys from the students, or to have students answer surveys and to understand their experience and how it can be improved or changed. And that will be in the fall.
Oh, headset.
Yeah, thanks. Thank you. Let's just stop recording and we can, anyone want to try out the 360 video, please come to us and this, and we also have other apps like the Ovation, which is public speaking one. Come on.
It's called the expert.
Okay, so here, everyone, I know, we actually.
Oh my god, thanks, Amazon.
Start trying it everything, yes,
On
yeah,
it later.
actually,
Oh my god, I know.
that's fine, yeah,
Yeah, you were supposed to show me this thing.
that's a quest this week, oh, yeah, that's.
Okay.
And, yeah, so we actually, if you come here. Okay, anyway, you can show them the frame VR.
That's.
Yeah, students can access it from computer as well, so if you want to take a look